Yeah. So are you able to see?
Okay, we can start, I suppose.
Yes.
Yes.
You can tell me.
Yes.
I'll change the slide.
Shall we?
Yes.
Yes.
Good morning. It's a pleasure to be talking to you, albeit from a remote distance. And as I was talking earlier, it's way too early for me to be talking or doing anything. I'm a night owl, a nishachar, as they would say. So being up at 7 o'clock is unusual thing, but it is celebrating Dr. B.K. Nayak, so I had no other option. In fact, if we had a live meeting, I probably would have shown up to enjoy the beginning of monsoons in Bombay at this time, which I have never done. So I'll talk about mm, nuclear incompressibility and why are some nuclei fluffy or something. So we'll talk about, you'll know what I mean. So let's go to the next slide, please.
Yes.
So you see these pictures. I have known now, I couldn't find a picture that old. I have known Nayak now for 30 years. The first time I met, I remember it was at the home of Rajnikant Chowdhury. He used to have a motorcycle at that time. And my 3-year-old son Neha really enjoyed riding with him on the motorcycle. And then worked with us. He came to Notre Dame in 2001, and these are pictures from his passport and his visa in 2001. So you can see, except for the mustache, he hasn't changed much. Anyway, so Dr. Nayak's expertise was in fission and surrogate reactions, and we were doing giant resonances, but he came and made many contributions. So here you see from one of his papers, where we saw the bimodal isoscalar giant dipole resonance in nickel 58. This was the first time a concentrated monopole or isoscalar dipole was observed in a nucleus as light as nickel 58. Before that, anything below 90 zirconium was considered not possible, etc. The next slide will show another picture, which is which he looked at the decay of the isoscalar giant dipole resonance in lead 208. Again, this was a very difficult measurement, but we managed to get very good results out. And one of the lower picture in the right hand side has been used many times, because we through this we show the actual shape of the isoscalar dipole, and we were able to show that anything at high energy that we see in single spectra was not really from the resonance, but from other effects. So we had a very productive time. He got involved with many other experiments. Next, please. Can you go to the next slide, please?
Yes.
Oh, something is missing there. So I can tell you, Dr. Nayak in 2 trips spent a total of 29 months with us. In these 29 months, we managed to produce 28 papers together, including 12 letters. So it was a very productive collaboration, and I'm grateful for that. With that, I'll start talking about nuclear incompressibility. So what is nuclear incompressibility? It is how far you can compress the nucleus. Next slide, please. So what one sees is the nuclear equation of state and compressibility. Next slide, please. Compressibility is the second derivative of this, the curvature of this equation of state. And you can see, if the curvature is smaller or larger, we call them soft or stiff nuclear incompressibility. Next, please. Now, keep going one by one. It's, aha,
Oh,
somebody else is coming in between.
okay. I think it is. Is it okay?
So nuclear incompressibility is an important component of nuclear equation of state, and that e- equation, it has important consequences in many things. I don't see the pictures, but hopefully you are seeing.
Yeah.
explains the neutron stars, the stellar collapses, supernova explosions, and high energy heavy ion collisions. So all of these are where nuclear incompressibility comes into picture. Next slide,
Presentation is
please.
not visible anymore.
Huh? It's not visible.
No, the presentation is vanished. Somebody interrupted
Actually,
something else.
I'm also not able to see the presentation. I'm also not able to see the
That's what I
presentation.
said to her.
I'll maybe probably I'll restart. I think. Okay, I'll restart.
No, I think they have to pin Satrada, no? You have to pin Satrada, then only.
Okay, let me try again.
कैसे करना है?
You see the list of participants, no? There you pin.
Okay, that is
Okay.
the first slide. No, not that. Yeah, actually somebody joined and presentation mode they started.
Now can you see?
I can see Satrada slides, I can see. Huh? So they have to pin, I think. That's it. They are seeing somebody else's screen.
But it
Okay.
has to be made full screen.
Yeah. So
Yeah. So pin Satyarajan Satra.
yeah. Are you able to see now?
No.
Yes, I can see.
अच्छा हाँ,
Yeah, we can see.
Kripa has told na I did the same thing. I pinned Sandra. Now I'm able to see it.
You have to pin down Sandra.
Ah yes.
Yes.
Yeah. After pinning Sandra, I could see.
Okay. Now
Okay, where are we?
Yeah, nuclear incompressibility. Nuclear equation
उससे
of
पहले की
state.
स्लाइड एक बता दिखा देंगे हमको कि नहीं थी.
There is a
You can go
movie,
to
I
the
think,
next
no?
slide.
Mic is on. There is a lot of
Huh,
echo.
huh, yes.
I'm not able to see the.
There is a movie. I
Movie.
think there is a movie or something like that.
Where?
And that is
Professor
causing the
Garg?
problem?
Yeah,
Yeah.
there is a movie, no? In your slide.
No.
Yes, next.
No.
So actually now when
We can skip the
when
slide.
Dr. Appanna Babu joined,
Huh.
I think at that point that started some problem.
Aparna Babu, you
So,
can stop presenting
Appanna
it.
Babu can
So whoever is a host should make sure that participants don't have presentation rights except for the chosen ones.
now Appanna Babu, can you come out of your presentations and just re-watch? Yeah. Now
Okay,
can
he
you
has
try?
left the meeting.
You'll rejoin with the normal option.
So now can everyone see?
No, sir.
Not yet.
Again, you can, Sandra, again you can reload.
Okay. Yeah. Right. May do that.
No, but we are about to see. Means like,
Yeah, we are able to see.
Samsada, you asked
Ah.
everybody to pin your.
Okay. What I'll do? Maybe I'll try again. Huh?
The pin, we can see the presentation, not the speaker. We need both.
Okay.
Will come.
Professor Garg might try himself, right?
Shall I
What is
try
the problem?
again?
I think you can try.
Yes.
No, let me do
And keep
it.
the mic
I'm
low.
open.
Other
I am trying again. Can everybody see? Now is it coming in everybody's screen?
Yeah, you note now.
Okay.
Yes.
Okay.
Yes.
Okay. So this is now this page, isoscalar giant monopole resonance, I equal to 0.
All right, that's fine. I
Yeah.
don't see it, but I'll start talking. Is everybody seeing it?
Yes.
I think everybody should see because now I have reloaded. Yeah, you can.
Okay.
Yeah, you can carry on. Dr. Pillai, you can see it?
Keeps telling me I am presenting. Let me get out of here somehow. Stop presenting.
Yeah, stop that. That is why you are not able to see, I think.
Yeah, okay. All right. I see something. So the isoscalar giant, the only way to
Kindly
measure
share the
nuclear
screen.
incompressibility is the isoscalar giant monopole resonance and the isoscalar giant dipole resonance. The monopole resonance is the breathing mode where you can see the nucleus breathing, and the energy of this monopole is directly proportional to the square root of the compressibility. Next slide, please.
Yeah. Yes, the graph is shown.
Oh, it was okay. I don't see anything, unfortunately. All right. The way you measure these resonances is looking at inelastic alpha scattering at very, very small angles. You can see in this figure, the black line is the giant monopole resonance. The purplish looking line is the quadrupole resonance. The red looking line is the dipole resonance. And if you look at them, for example, compare the black and purple, you see that the two resonances differ.
They don't see anything.
Is it?
Kindly share the screen. You have not shared the screen. Kindly share the screen.
No. Those who are not able to see the screen, please go at the grid of Dr. Satyaranjan Santra and click on that pin. Click on that pin.
I
Even
have
after
done that.
pinning, I was not able to see him now.
I am able to see.
Yeah, I am able to see.
Actually, most of the people can see, so talk should probably proceed.
We can see it.
If you pin, it comes on the screen. If you are not able to see, that means your internet is slow. Yes.
Yeah.
Oh, that's another problem.
And you
Shall I continue?
have you stopped presenting, Professor Gaur? Have you stopped presenting? You have come out of your
I'm not
presentation?
doing anything. Santra Saab is doing my presentation.
No. Sometime back you said no. Still presenting mode is there, so you have to go out.
No, I'm not doing anything. I'm out of everything.
Okay. Now what about others?
It is visible.
Okay.
I can see.
Yeah, it's okay.
Yeah, it's
It is
visible.
working.
Yeah,
It is
maybe.
working. You can go ahead. I
Okay.
think if
Somehow
you
one
go
has to
to,
pin the slide.
You can go to Santra presentation and click. Then it is working.
Yeah. Okay.
Go to Santra presentation. He has
Yeah,
two,
please go ahead. Actually, Professor Garg, please go ahead.
Okay. So, again, you are seeing the angular distribution. The point I was trying to make, that one has to make measurements at very small angles, including 0 degree, to measure the monopole resonance. We do it with inelastic alpha scattering at 400 MeV, and we do these measurements at Research Center for Nuclear Physics, Osaka University. Okay, next slide, please.
Yes.
Feels like going back to 70s when we used to have somebody moving the slides.
Yes.
Has it moved?
Yes, it has moved.
Okay.
Well,
I
it's-
guess I'll take your word for it because I can't see it. So this is RCNP Osaka. They make up to 400 MeV alpha particles. They come through two cyclotrons, and finally you end up with what is known as the Grand Radon spectrometer. Grand Radon is, you can see the spectrometer is a big beast. It's a very, very good and useful spectrometer. The Radon stands for the name of a sumo wrestler because it's big. They went for a Radon was a sumo wrestler, and when they made a Grand Radon, that means a bigger spectrometer. This spectrometer can allows us to measure high resolution at the focal plane measurements, and it also gives another property that I'll talk about. Next slide, please.
Yes, that on photograph is there. Shall I go to next or?
All right, let's just keep going.
Okay. Yeah. Now graph phase 240 MeV
Alright.
alpha prime.
This is just to quickly tell you one of the properties of the Grand Radon is that we can get rid of instrumental background. Some of you might remember the giant resonance spectra looks something like this. In fact, Dr. Bensi has worked with such spectra. So what one saw a huge background, and one used what is called a reasonable background subtraction from this. Now, reasonable is a very unreasonable word because you can choose in many different ways. Of course, they develop techniques to choose the right background, etc. But this was always a source of problems, complaints, uncertainties, etc. So what the grand radon allows us is to completely eliminate the physical background. Then we don't have to do any sort of subtraction. Next slide, please.
Yes.
What the grand radon allows us to look at the y direction, and in the y direction it focuses all particles coming from the target and defocuses anything which comes from the scattering. Most of this instrumental background is further scattering of elastic scattering data, and we can separate it out. If you look at the upper right hand picture, you see the original picture and the instrumental background below. So without this instrumental background, we would have to draw a background and try to subtract, as I showed in the past picture. Now you don't have to do it, and you get a subtracted spectrum, which is in the lower picture. And you see that it has all the instrumental background has gone away. Whatever you see is the real resonances plus the excitation of the real continuum, which we can take. So what we do is we take these background subtracted spectra and do a multipole decomposition at various parts of the spectra. Next slide, please.
Yes, 112%.
Now, multipole decomposition is basically looking at the angular distribution and fitting them to the combination of the various multipoles, the angular distributions I had shown you before. From this, we can, at various excitation energy, find the contributions from various multipoles, and that can give us this information that we are looking for. And that's how we extract the strength distribution. Now, of course, normally I show a beautiful dance here at this time to show you how the multipole decomposition works, but unfortunately you'll have to wait for my next talk sometime. Next slide, please.
Yes, 90 zirconium.
So once you have the angular distributions, etc., you can extract the strength distribution, and in this picture I have shown you strength distributions in 3 nuclei. This is the monopole resonance in lead 208, tin 112, and zirconium tin 116 and zirconium 90. And as you can see, this is very nice concentrated resonances. So now we have the giant monopole resonance. From this resonance we can get what is known as Ka, compressibility of a nucleus. From there, but what we are after is K infinity, which is compressibility of infinite nuclear matter. Next slide, please.
Okay, from Ka to K infinity.
Yes, from Ka to K infinity. So the way to do it now is you build some energy functionals, and each functional has parameters, and one of those parameters is K infinity. What one does is obtain GMR strength distributions in a self-consistent RPA calculation. And what one finds is, fortuitously or really, that Ka and K infinity have almost a linear relationship. So once you have determined experimental Ka, you can easily get K infinity from this. Unfortunately, I can't show any pointers, etc. So if you know Ka, you would be able to see K infinity. Next slide, please.
Yes. Done.
And this is an example where you see that the monopole resonance calculations by various theoretical measures, and if you compare the peaks, the 2 lines are the experimental limits, and you see that all these calculations reproduce the centroid where I have measured it, and that is how you figured out. So these 3 would be an acceptable. They are for 225, 230, and a 251, which you can see is slightly higher. So that's how we get K infinity. Next slide, please.
Yes.
So from giant monopole resonance data, we typically look at lead 208 and zirconium 90, the canonical doubly closed shell nuclei, and we get a value 240 plus minus 20. This number is consistent with monopole resonance, the isoscalar dipole resonance, relativistic calculation, non-relativistic calculations. And if anybody asks you today, what is the value of nuclear incompressibility, the number is 240 plus minus 20. Next slide, please.
Yes.
Now, once you have this, we found a very interesting problem in the tin nuclei. What I am showing here is the centroid energies of a number of tin nuclei from 112 to 124. These are the data with error bars. I also show you two calculations. The calculation of these centroids within the RPA from two interactions, both of which were able to reproduce the lead and the zirconium. That means they belong in the category of 240 plus minus 20. And you notice that the tin are lower energies. That means if we used tin to do our measurements, we'll come up with the K infinity, which is lower. So why are tins fluffy? Or I think when the paper was first written, the editors didn't like the word fluffy. They said it, why are they so soft? So this problem as to why when I use 240 plus minus 20, I am overestimating the tin nuclei. That is what I meant by fluffy. Please, next slide.
Yes.
The same problem existed for the cadmium nuclei. And it's the same thing that you see that the data is at the bottom, and there are 3 or 4 different calculations that we have done between various interactions, and all of them overestimate the nuclei. Of course, NL3, one can forget about it. That's the topmost. That has a very high 270 MeV compressibility, but all the other 3, FSU, gold, SLY5, and including with pairing, they do not reproduce this well. So this is the fluffiness problem, which we first noticed in the tin isotopes, and then when we measured the cadmium isotopes, they reappeared again. Next slide, please.
Yes.
Now this has remained a problem. The first thought was that, well, you are out of closed shell, so you need to take into account pairing, or as a sophisticated word to be used was superfluidity. And in this particular case, you see the experiment versus calculations which include pairing, and it did not, and it also used a K infinity of 215, which is a little bit low, but it's still, they were not able to reproduce these energies for the tin isotopes, and this problem remained. Next slide, please.
Yes.
This is, are we here?
Yes, yes.
Yeah, this is a much more detailed calculation for a huge number of tin and lead isotopes. And you see here that the calculation for lead is more or less reproducing the experimental data, but the tin are way above the experimental data. So this includes pairing. This is SLY4 interaction, which one finds very, very useful, but one still sees that in all tin isotopes, going right from tin 100 to whatever, one does not find the reproduction of the tin nuclei from any theory. And this is the problem of fluffiness of the next slide, please.
Yes.
This is one theoretical calculation which tried to explain this, and here they have reproduced the experimental data with their calculations, and you can see it's a beautiful representation. It's self-consistent Hartree-Fock plus BCS, but they use T5 Skirm interaction. T5 has a K infinity of 202 MeV. So you can reproduce the tin isotopes but you need a K infinity of about 200 MeV, and that is what the same problem. If you can read at the bottom, it says on the whole we cannot settle the ambiguity and K infinity as value as before, but we just wanted to see how would the tin be properly reproduced. And you see the tin requires 200 MeV. Go ahead, please. Next one.
Yes.
So this is one more calculations where what they tried to do is they forced the data to fit the tin nuclei, where they used K infinity 230 kV but changed some other parameters and tried to reproduce the tin data, which you can see the red line. It reasonably reproduced the tin data, but when they did it, the lead was out of order. That required lead to be much lesser by 1 MeV. So the moral of the story was that the theory has not been able to reproduce the tin and cadmium nuclei if by using what we consider the K infinity, which we always obtain from lead 208 and zirconium 90. Next slide, please.
Yes.
So there were many interesting ideas about what you can do, and one of them was what was known as mutual enhancement magicities. It turns out that if you have a doubly magic nucleus, there is an extra stability that comes, and this has been an effect which is known for a long time. This paper is from 1983. What it shows is that, next slide please.
Yes.
What it shows is that if you just look at these are separation energies, etc., all I want for n equal to 186, I want you to look at near 82, and you see that all the calculations are off from the experimental data significantly at n equal to 82. This difference is very well recorded and significantly measured. Next slide, please.
Yes.
This is the same thing for n equal to 82, and you see the same effect at z equal to 50. That at z equal to 50, the calculations do not reproduce the separation energy well. So this maximum mutual enhancement of magicity was an effect well known. So the idea was that if these guys are extra stable, maybe they are also extra incompressible. That means for doubly magic nuclei, you would have extra incompressibility, and that's what we are seeing because we are calculating everything from doubly magic. When we go out of doubly magic, we have this effect. So there was, next slide please, there was some calculations which were done, and it was speculated that if you look at lead 208 versus the nearby nuclei 204, 26, 10 to 12, you would see a decrease in the monopole energy. This figure shows monopole energies as a function of mass, and you can see that it reproduced the lead energy quite well, and the prediction was that the lead 204, 206, 210, 212 would be lower in energy because of this mutual enhancement of magicity. Next slide, please.
Yes.
We tested this by looking at 3 lead isotopes that we could measure, 204, 206, 208. And in this picture, what you see is 3, I think there's a green, a red, and a black. If you can figure out, these are just 0-degree spectra from the 3 nuclei, and you can see there's no difference between them. Next slide, please.
Yes.
Okay, so now what do we have? This is the same thing. You extract the monopole strengths the way we have gone through, and you find that 206, 208, 204 have exactly the same energy. So the idea that mutual enhancement magicity was affecting this is not tenable. So in this particular case, the theory would have expected at least about 0.5 MeV difference. We do not see any difference. So this problem, again, next slide please, has remained, and that's what we wanted to explore further. So we measured the moly isotopes. So remember, we're talking about zirconium-90 as a doubly closed nucleus. So the next isotope we can look at is moly. So we made measurements from moly-92 to 100. So these are spectra showing only from 94 to 100. It's not important. 92 was done earlier. So we have taken the same data the same way simultaneously for all the moly isotopes. Next slide, please.
Yes.
And these are just some of the angular distributions, etc., so that you know that some people have done some hard work. By the way, Dr. Yogesh Gupta was involved in the very first measurements we did on moly-92 and later on these things. Okay, so now you have, next slide please.
Yes.
In this, we show you the monopole strength distributions for all the moly isotopes. I also show you one of the cadmiums, one of the tins, and the lead-208. What I want you to notice, and the red lines are theoretical calculations using what is known as FSU Garnet. What I want you to see is that the lead position is very nicely reproduced by the theory, and moly is also very reasonably reproduced. Though the zirconium, which is the very top left corner. So go look at the top left corner and bottom right hand corner, and you find that this interaction reproduces lead very, very well, zirconium reasonably. Now you start looking at the molys, and in all cases what you find that the experimental peak is below what the theory is predicting. And that is again what we were talking about, the softness. So the point is that the softness is appearing as soon as you get out of the closed shell. Moly is just about, we start with moly-92, which is 2 nucleons away from the what we are calling doubly shell nuclei. So the next slide please.
Yes.
So that picture just is a comparison. So what you look at, the experiment and the theory. The red is theory, black is experiment. As you can see, at lead they completely match, and in between you see the zirconium-92, moly-92, moly-94, etc., and you see that there is this difference, the softness which is maximum at 100 moly, and it continues. And that is still something which is bothering us. We still do not know that this appears at 92 zirconium and 92 moly. So we are talking about just 2 protons or 2 neutrons out of 90 zirconium, and this softness appears. And I think this is where I leave is as a challenge to all the theorists among you, if you can help us find out as to what causes this fluffiness, this softness in nuclear incompressibility as we leave the doubly closed shell. So it's very clear that what we get is incompressibility from these nuclei which we consider doubly closed, lead-208, zirconium-90, I call them the canonical doubly closed nuclei, that does not work for anything else. And that's where we come, I think, more or less to the end of this talk. Next slide, please.
Yes.
So that is what I leave you with to ponder. And again, to all theorists in you, if you have some ideas, we are very, very open to it. Not only that, we are desperately looking for trying to figure something out. To summarize my talk, we have investigated the isoscalar giant monopole resonance in moly isotopes via an elastic scattering of alpha particles, 400 MeV at extreme forward angles. In the tin and cadmium isotopes, we had noticed that the isoscalar monopole energy was lower than what you expected from the accepted value of K infinity. And normally I ask my audience here, does anybody remember the expected value? So some of you do, 240 plus minus 20. And this is the question of fluffiness of open shell nuclei. This fluffiness appears in Moly isotopes beginning with 92 Moly, which is just 2 nucleons out of the doubly closed nucleus. I hope one of you will pick up the gauntlet of trying to find a satisfactory explanation of this phenomenon. Next slide, please. So I am at the end of my talk. I want to just thank all the collaborators we have. You'll recognize at least one name in the first line. I particularly want to point out the people whose names are underlined. These are the people who did most of the work. And the 2 red colored are undergraduate students, which again, I always like to point them out separately. Specifically, we have undergraduate students involved in our research. They make very, very important contributions and become our co-authors. So with that, next slide, please.
Yes.
I thank you and say dhanyavad. And I do not know how it works, but I'm open for any questions, comments. Next slide, please.
Yes.
And this is my question kitten. If you ask nasty questions, somebody jumps at you. Thank you. Thank you very much, everyone.
Thank you, Professor Umeshkar, for this excellent presentation. And of course, I'm sure that you may have several questions, and you can post that questions and mention the name of the questionnaire. So then I post that question.
No, those who are in YouTube, they can post, but those who are Google Meet, they can unmute themselves and ask. I think it is okay.
Perhaps.
Can I stop? Can I ask a question, Umesh?
Yes, go ahead.
Yeah, this is a question to Umesh. Just one or two slides before, when you showed the deviation of the energy from molybdenum 92 onwards, and then it started increasing up to molybdenum 100, and then the difference starts again going down. So is it giving some signal to what the spin effects are doing?
Santra Saab, can you go back couple of slides?
Yes. Which one?
You'll figure out which one it is. This one is what. Okay. The interesting issues. Of course, we are going to moly and then we are going to cadmium and tin, so the slight difference comes from there. But one of the things which I did not allude to in this, can we go one more slide behind? Yes, please. This is the right one.
Yeah.
So if you notice the 98 and 100 moly. No, please go further. Whatever slide you are showing, I want to show the actual monopole distributions.
This.
One more. Yeah. No. Forward, not backwards. Forward, please. I
This
want
is
to
done.
show the strength distributions in the moly.
Yeah, this is molybdenum isotopes. This is experiment
Okay, I don't see it,
experiment minus theory, right?
Everybody seeing the strength distributions with the
No.
calculations?
No, this is the difference one. This is ISGMR,
This is energy belt.
and
Maybe this one, Santrada.
d square sigma by d omega de.
After this,
Yeah.
No, this
Now
is
it's-
MDM.
This is again d square sigma.
keep
Yes.
going. No, we are going
This is
backwards.
lead.
We're going backwards. We should go forward.
No.
Okay, this is cross section ISGMR, then experiment minus theory.
Okay.
No.
If you show this, it's okay. Just before this one.
Yeah, this is ISGMR strength.
Okay, beautiful. That's the one. Yeah, I see it now. So what I wanted to point out was that if you look at particularly 98 and 100, the resonance has 2 bumps. And this is because these are deformed nuclei. So because of the deformation, there is an extra component of the monopole and the centroid goes down much more than it is. So yeah, the way to compare maybe we should have done is just the upper peak. Then the difference that you see in the next is not as much, it's about the same. Next slide, please.
Yeah, this gives difference between experiment
Yes.
and.
So what you see is here is that this difference for 98 and 100 is probably artificial in the sense that some of it is coming from deformation also. But the 92, 94, etc., those are up to 94, 96. There's no deformation, so that effect is still very much there.
Okay.
Have I answered your question, Rajnikant?
Yes, please.
Is there any other question? You said you had two.
Yes, sir. I have a question.
Okay.
Myself, we can have. My question is, you correlated that for closed cell nuclei, we are finding a difference. We know that closed cell means those nuclei are very tightly bound. So, is there any correlation?
Well, that is the question that we tried to do with the maximum enhancement of magicity tests. That was originally the idea suggested, that what it is that because the two are closely bound and because they have this extra doubly magic enhancement, maybe it shows up in compressibility also. And that direct effect would have been on lead 208, 204, 206. And we did not see that effect right there. Okay? So it is the same thing. In fact, that's an interesting point here from zirconium 90, we already saw the effect in zirconium 92. But in lead 26, we do not see.
Okay.
So there's difference between probably zirconium 90 and lead 208 also. Again, the experimental data is what it is. I think the theorists have to figure out what it is.
Ramesh, delay here.
Yes.
So the thing is that
Yes,
since
Lekha.
you're correlating it with this magic shell and open shell and so on and so forth, have you ever plotted the same data against the, say, separation energy or something, and look for correlation with it?
I think that's a very good idea. We have not done it. I think that we just think it is that way. I have truly, and nobody has any idea what exactly it is happening. What I'm trying to say in this particular case is that theorists, when you give them, they need to extract nuclear incompressibility, they like to deal with lead 208, etc. As Jerry Brown would say, there are only 4 nuclei. What did he say? Oxygen 18, calcium 40, and lead 208, and probably alpha particle. Everything else is a matter of detail. So I think it's the same way they are happy doing calculations for lead 208, and then include zirconium 90 in one of these, and that's how they come up with 240 plus minus 20. So something else is happening. If we want
But open shell nuclei, for example, there are many parameters. You can look at the.
Yeah. That's why most of the parameters
Any one of them which is sort of a signature of open shell, and we plot it again.
So you are right. We have not done it, but this is something I think I'll have Kevin do it tonight. So that is, we can try to plot them with respect to, say, separation energies, etc. I think it was done in terms of, in case of lead, and that one did not see a pattern. But it would be a good thing to look at. Thank you. We will.
Bye.
I have a question. I am Ramachandran from BRC. So the beam energy, I think you were saying like 386, 400 MeV kind of thing. So the excitation energy, I believe it is high. So in that case, the cell effects are supposed to vanish, no? So how is it the cell effects having an effect here?
Yeah, you're right. With the excitation energy of these guys are 15 to 20 MeV, and yes, there should not be any shell effect. That is the problem. The idea is that for these resonances, they're supposed to be completely independent. These are collective phenomena. So they should only be depending on a raised to 1/3. But it's not. And that is the open problem. That is the fluffiness problem that we want to deal with. By the way, this little one, how old is he? I see a picture of you with the little one.
That's my daughter. It was taken like 4 or 5 years back. Thank you.
Okay. Looks very cute.
Yeah, thank you.
Any other questions? Well, I suppose then I thank all of you for putting up with all the problems, all the issues with this talk and whatever else. Thanks again to all the organizers, and I bid you goodbye.
Thank you so much, Professor Garg. It was an excellent presentation, and you have taken us through this teething trouble of this Google Meet meeting we have, and you have been always doing that very kindly to many of our members in Indian nuclear physics community. And thank you so much once again. And
Again,
now,
I apologize for whatever, if I caused any problems, but it has been a pleasure. And as I said, for Nayak, I woke up and now I can go back to sleep. Thank you, everybody.
thank you so much. Yeah, we have now with the first talk we are through, and let's go to the second seminar of today. That's a comparison of fusion cross sections for 32 sulfur plus 182 184 tungsten reactions, along with the statistical model calculations. And this seminar is given by Professor A.M. Vinod Kumar, Professor and Head, Department of Physics, Calicut University. And Professor Vinod Kumar is, in IUSC, is associate of IUSC, and he has done his works in several laboratories over the world. And Professor Vinod Kumar now invited to present his seminar.
Good evening.
Yes.
Can everybody can hear?
Yes, we can hear you.
Yeah, yes, we can hear. And your slide, we are looking forward for your slide.
I will, Sandra will present
Yes.
my slides.
Yes.
Okay.
I'll change the slides whenever you tell.
Okay. Good evening, everyone who are attending this through Google Meet, as well as those who are watching it on YouTube. So this, first of all, I would like to thank the organizers of this webinar, especially the NPD BRC and other members who are on the occasion of Dr. Naik's birthday, 60th birthday. And so here in this talk, what I wanted to tell is a small problem which has been existing from or bothering me from maybe for the last 10 years. So this is what I wanted to share with you is the 32 sulfur with 182 tungsten and 184 tungsten fusion reactions. So this capture as well as evaporation residue cross sections has been measured at different laboratories, and we would like to see how we can consistently compare these measurements with the model calculations. Next slide.
Yes.
I can't see.
Can others see?
I can't see the next. It is still not changing.
Yes.
No, actually, Sandra, actually what happened even in last one, no, most
Huh.
of us could not see the changes. It was changing very slowly.
So I
there
go
was
to my
lag.
slide and, okay, I go to my slide and you can move on to the next one, sure.
No, but unless it is visible to others, I think it will not have any
It will be
meaning.
good if the speaker himself is sharing the screen.
No, there is some problem. There is
That's
some.
ideal, but if it is not workable, then there are against Santra there are 2 entries in if you see the participant.
Yeah.
And
No,
in one entry you will see the slide and
Yeah,
pin on that.
presentation.
Just pin, then it becomes smooth.
So
No, it
can
is
I?
not because of the cooling. We are able to see
Can-
the slide. The first slide, the change is not happening.
Slides are not changing.
Yeah, that
Can we,
is.
can we try once at least speaker to change the slides?
Okay.
Yeah.
Okay, I'll.
Stop and I will present myself.
Yeah.
Please.
Okay.
Yeah.
So you're stopping.
Yeah, I'll stop it. Stop.
Okay.
Yeah.
Can I?
Yes, you can start. You can present now.
Can you see the first slide?
Yes, yes.
Okay.
We can see that.
Yeah, fine.
Okay. So I go.
Yes.
So in this presentation, so I will first compare the capture cross section for 32 sulfur on 182 and 184 tungsten reactions, and then compare their evaporation residue cross section, and we do statistical model calculation using HIVAP code, and we compare the results and discuss about how these fission barriers and whether the energy dependent one can explain, and also we have other calculation from DNS model and DCM models and how they compare with this cross section. So as I said, this was in 2011, we put up a DA contribution where we have compared the evaporation residue cross section measured by BBPAC at Argonne National Lab for 32 sulfur on 184 tungsten, and Mitsuoka et al. Measured 182 tungsten evaporation residues. So you can see that green one is for 214 thorium compound nucleus, which has compound nucleus have 124 neutrons, and the other one is 126, which is the back measurements. So there are other curves which are DNS and other things which was available that time, and I have put. So what is the main point is, you can see only in the compound nucleus only 2 neutron difference is there, and of course it is 126, so the neutron number. Now the difference is huge. 2 numbers of tungsten nuclei have 2 neutron difference in these target nuclei, and you see the ER cross section is at more than order of magnitude different. And of course the more problem is their 184 case, the models are not able to predict even the shape. So you can see the next slide.
Yes.
Hello?
Yes.
Yes, we can see.
Okay. Now this is the, so we asked the question for n is equal to 126 in the evaporation residue cross section, do you expect any additional stability or this cross section, why they are so different? So look back into the old literature, you see the thought here in the left plot, this is maximum cross section for foreign evaporation channels has been plotted in a taking care of the inter-channel effects, and this is taken from this sound paper in Nuclear Physics 1985. You can see these experimental, the points are the experimental ones. You don't see any specific enhancement or differences in the observations. So there is no additional stability or other things are not shown here in the experimental. Of course, they have calculated the fusion probability, which is on the right side. In the right side plot, you can see they compared 220 thorium forming using argon and 124 tin with the zirconium forming 220 thorium, and the fusion probability has been compared. So I don't want to discuss that one, but what you have is in the left side is n is equal to 126. You don't see any large differences between these things. Now,
কি পায়খানা করলো নাকি?
Measurement from IUC, Punjab University, Vivash already he is attending this. So this is from their group, measurements done at IUSC. This is evaporation residue measured for fluorine on platinum. So here the compound nucleus formed were 213 francium and 215 and 270. So N is equal to 126 in the compound nucleus and others are 128 and 110. So here in the evaporation residue cross section, what you see is the cross section for 213 francium is lower than other 215 and 270. So you ask the question, why this is like this? So are you expecting the evaporation residue cross section to be small compared to the 130 and 128? That's a question was asked. So now they have, so before going this, probably this, if one see this paper, they have analyzed using changing the fission barriers and energy dependent fission barrier like that and explain the cross sections. So in going this to those who are maybe the students community who are, so these are the formulas involved in evaporation residue cross section. So you have compound nucleus thing with the survival, and sigma compound nucleus can be provided by sigma capture into PCN this way. So here there are three spin dependent quantities: capture cross section, fusion probability, and survival probability. So now my way of dealing with this problem is look at the 32 sulfur on 182 tungsten data. So here in this plot, what we have shown is the data from Mitsuoka and Shang et al. They are measured for these things here, and you can see that 182 and 184 is compared here. So capture cross section, you can see that feasible calculation in a represented in a good way, shape wise and magnitude wise. You can see that there it's a well represented the capture cross section. So there is no ambiguity or anything in the capture cross section if you do feasible calculation. Now this was okay. I can skip this. Now look at the 32 sulfur on 182 data along with the evaporation residue cross section. So here I have plotted the top blue ones are blue points are the capture cross section, and black points are the evaporation residue cross section. So you can see that the capture cross section for this system is well represented as we have seen in the previous slide, and now evaporation residue cross sections, you see they are reasonably well reproduced if you scale with a factor of PCN is equal to 0.75. Of course, there are some sort of change in the shape and all this thing, but I will compare the 184, then you will realize that how much it is different for the 184 and here 182. So to check this one, we have done statistical model calculation using a HiVAP code, as I said, and here these are individual channels. These are measured by Mitsuoka, and the red curves which shows our calculations, and it's better than the Mitsuoka's calculation, statistical model calculation, I presume. And the same compound nucleus is formed with the cysteine nickel and samarium. This case also we repeated the calculations using the statistical model code, and you can see red curves are our calculations, and the black dotted lines are Mitsuoka's calculation. So they are our calculations are closer to the experimental data. Now, if you look at other theoretical models, predictions for 182 tungsten data, you will see that DNS model calculations shown by dashed lines, and our ER cross section we have shown as dashed green lines. You can see that there are other model predictions that they were deviating from the evaporation cross section, but our calculations are very close to the experimental data. Now, so there are other PCN comparison with the DNS model and DCM. Recently, there was a paper from Manoj Sharma. He is attending this conference, I presume, and their paper, they plot the PCN from DNS model along with their calculation, DCM. So here, if you compare these things, the PCN numbers are more or less same, and the left side you see for it is 32 sulfur on 184 and the for 182. The other right hand side, this is a comparison from I have taken from Kaur and Sharma recent paper. So to go further, what we have done is so calculate for 32 sulfur on 182 tungsten and fix the parameters of the HIVAP code and look how it will look like for a 32 sulfur on 184 tungsten calculations. So you can see here the black points here, which is 32 sulfur on 182, and the red point square, which is the 184 data. So if you look at the fixed parameters for 182 and try to reproduce, do the calculation for 184, you see these dashed lines, red dashed lines, which is even after taking care of PCN, that's the energy dependent PCN, which is shown earlier, which cannot reproduce the experimental data for 184 tungsten. So I have put this in here now along with the capture cross section for 184. So you can see capture is well reproduced by the curve, red curve, which is on the top, and black points are the evaporation density cross section measured by BB bag, and HIVAP calculations are red line and green one is fusion plot. But evaporation density cross section, you can see that they are only reproducing the lowest two energy points. Higher energy points are not reproduced by this thing. So these are dashed ones are using 182 parameter set, and we have improved the parameter set to reproduce this one. So the red ones are obtained using a different parameter set in the code for 184W. So you can see that still we are only able to reproduce or get closer to the experiment at lower energy points. Now, here again I am showing the 184 system where you can see that the work I was mentioning from the DCM group, they have shown something here. You can see that they are shown by green dashed line, dashed dotted line, and which is not coming close to the ER, but the shape wise it is coming close. So I have divided by a factor 133, so you can get closer to the data. So after all, this dynamic cluster model somehow gives a shape wise the cross section in a good way. Other things, DNS model or HIVAP is not able to explain the cross section measured. So in this plot, the same 184 cross section has been using an energy dependent fission barrier we use. This is the same work as if you can see the original work by BB Beck. Their statistical model calculations they have done varying the fission barrier. So if you look at the fission barrier obtained from this fitting, you can see fission barrier scaling factor versus excitation energy. You see that if you go to higher excitation energy, you are getting even up to 1.8 times the liquid drop fission barrier. A very large variation in the fission barrier, which is required to explain the cross sections. Now, so that was, now we asked the question, so if there is a collective enhancement of level densities, and so if you look at the literature, if you see this pioneer work by Jugans, and there they measured for fragmentation, they could calculate and explain the fragmentation data for these thorium isotope, and they find that it is a significantly improved the calculation once you apply the collective enhancement of level densities. So also there are other works in the ER itself, collective enhancement of level density. I am not mentioning all the work here, but if you see this one from IRO and in 2014, which compared two measurements, their own measurement 159 dB and 48 calcium on 159 dB, and also they have taken Mahata from BRC group's work, that is forming fluorine, 19 fluorine on osmium, forming the same homonucleus. So their argument is that this the agreement, once you include the collective enhancement of level density in the calculations, and it will be better. So these are the calculations they show by including collective enhancement of level density. They could explain the evaporation residue cross section in a better way. Now, there are other efforts by various groups in looking at it, but many of them has not observed any collective enhancement of level density. This is from Sagadai and Andreev in 2009, and they have compiled many of the data, and they shown here bottom plot. If you see that, only you can say fission barrier, which is for close to n is equal to 126. There is no drastic change in the fission barrier for close to n is equal to 126. Okay, that's the point I want to take. This is an analysis of various systems using statistical model calculation, but they varied the fission barrier height and different values. Okay, now if you say that still collective enhancement may be a problem, so I look at the thorium isotope specifically and look at here these circled ones. If you see, circled ones is 124 and 126. You see the values are, these are not much different. So the order of magnitude difference what you see here, it could have been at this point at 120 or this side. If there is a drastic difference in this collective enhancement, but here 124 and 126 don't see the difference in these things. So my point is that these can, after all, these effects can give you maybe a factor of 1.5 or 2 in the cross section, but not this big. Okay, that's my point. Also, you one look at fission barriers for thorium isotope using different models, and Cohen-Plasil and CIRP model, all these table what you Peter Moller. If we see these 214 and 216, you see the differences are very small. Okay, so the fission barrier, even if you don't fit that data, you get these numbers from different models. You see the difference is very small. So this is not going to give you that big difference in the ER cross section. So I think my main objective is to introduce these differences in what calculation I was doing, and my point is that the collective enhancement of level density, that may be one point one would have thought, but if you look at the things, it is not like that. So I, let's say, to conclude this talk, I will say 32 sulfur on 182 and 184 tungsten fusion ERs and capture cross section compared, and ERs cannot be reproduced with the statistical model calculation using 32 sulfur plus 182 tungsten parameters. PCN obtained from DNS model or DCM also fails to reproduce experimental ER cross section for 32 sulfur on 184 W. So to overall conclusion, I will say the comment, the lines which I borrow from Shang et al., it says the measured data for 32 sulfur on 184 tungsten could include evaporation residues that are formed at incomplete fusion or multinucleon transfer reaction at ECM greater than 160 MeV. This it is not my own conclusion, but I borrow it from Shang paper. Okay, so these are the things I wanted to talk in this webinar. And this work was been done with my student Sanila and in collaboration with the former faculty, Professor Babu from University of Calicut. And thank you all.
Thank you, Professor Vinod Kumar, for your presentation on the topic of fusion, incomplete fusion. And now this, there are, if you have some questions, let's ask Professor Vinod.
Can I ask a question?
Yes, go ahead.
Yeah, this is Mahata from BRC. So
Okay.
I'll just like to know what method was used for the measurement, because the cross sections are very small. So can you?
Okay. One is argon measurement, Argonne National Lab. It's a spectrometer measurement.
Mass spectrometer.
Yeah, spectrometer. And then other one is from Japan, and they both spectrometer plus alpha.
Okay. And your excitation energies are very large, so the nuclear dissipation will also have significant effect. Whether somebody has talked about it?
Yeah, I have not discussed it. There are energy issues are there, but still we are in the, let's say, 40 to 80 or 90 MeV excitation energy. It may extend to 120.
Yeah. No, because you were sometime commenting, that the excitation energy dependence cannot be reproduced by the HIVAP. No, so if the dissipation, increases the evaporation residue cross section, it also changes the energy dependence. So you can look into it.
Yes, but you can apply the PCN with the energy dependence, and that we have tried already. And there also it is also not able to get close to the cross section for 32 sulfur on 184.
Yeah, okay. One measurement wise also one should make sure, because they are measured at different labs. I do not know, because the cross sections are very low, 10 to the power minus 4 millibar, no? So one should also maybe check it.
It's there is a proposal approved at IUSC that's for 180 tungsten and 186 tungsten on 32 sulfur, and they're still waiting for the impact.
Okay. Thank you.
Myself,
Thank you.
Myself, DK Nayak, I just want to ask a question. My question is, you are trying to understand fusion evaporation process using HIVAP code. Whether fission measurement also are there for this system?
It's already capture is from fission.
But capture means so that is everything, capture means. No, what I'm telling, suppose instead of only trying to fit evaporation residue, if simultaneously you also fit a fusion cross section and evaporation. So that you will able to
simultaneously
fusion excitation and also evaporation cross section simultaneously, so that will be a constant to your optical.
इनका मीटिंग चल रहा है इसका.
Hello.
Join. You can also join.
Saxena ji mute कर दीजिए.
There is some noise, so I can't hear.
Okay.
No, Nayak ji, because this is highly fissile system, no? So the capture cross section is estimated from the fission cross section only.
Yeah, that's right. That's what I'm telling. If your fission cross section is too high, and you are trying to compare something too low, then you have to be very careful. So
Yeah, I agree on that point.
So if you want to do, then one should do simultaneously both the channels. So that may.
I mean, we can do such measurements.
Yeah, because you do simultaneously both evaporation and also fission. Okay, thank you.
Okay. Is any other questions?
Yeah, can I ask one question, Chaudhary here?
Yeah, please, sir.
This is a quite significant observation, and 2 neutrons away. One may not expect much change in the fission barrier, and also the measurements are done for both 182 and 184 in a similar manner. So whatever errors or uncertainties should be there in both. Now the question is it also you have studied this system, these two very extensively. Is there something, some other data with platinum or some close eyes?
Actually, that part also I am working on, but it is not concluded to let's say presentable things.
Okay, fine, thank you.
Other questions? If not, let's thank Professor Vinod Kumar for his very nice presentation, and we can move over to next topic. Before that,
Thank you. Thank you.
thank you so much. We can move on. Before that, any announcement regarding this YouTube?
Yes, hello.
Yes, announce.
YouTube viewers are complaining that few of the users are still switch off, did not switch off their camera. Due to that, they are getting very bad resolution and it is not running properly. So if everybody switch off their camera during the presentation, it will be
Very good.
Yes, of course. We request those who are on this Google Meet platform temporarily switch off your cameras so that YouTube viewers now they get better resolution.
As well as
And
mute
now-
yourself unless there is question.
Yes, mute yourself as well. And now we go over to the third seminar of today
No.
and the last one.
No,
of
is
today.
there any question in YouTube?
Hello. Yeah,
Some-
it seems from YouTube there was a question.
Some question.
Now, I was saying that take the question. See
Okay,
whether
yeah,
YouTube.
Yeah,
Just read that question.
Please.
Ananya, can you read the question?
No, see is in you.
Or whoever is
I
there.
don't know.
Uh,
If you can see,
Abhijit?
please read that question. I can't see.
YouTube में कोई question डाला क्या?
हाँ.
Okay.
There is a question.
YouTube channel.
That's
Hello.
not the question.
Yes, Prakash.
Some Seema Jadhav, sir, which type of code you are using for cross section measurement?
code you are using for
Calculation, okay. Measurement नहीं.
Calculation.
Okay, this is a statistical model code. HiVAP was used in this calculation.
Any other? Any other question, Shanath?
No.
Okay.
No,
Okay, thank you so much, everyone. And the third seminar is title is Determination of Hexadecapole Deformation of the Light Mass Nucleus 24 Magnesium using quasi-elastic measurements. This is presented by Dr. Yogesh Gupta from Nuclear Physics Division, BRC. Dr. Gupta has done his PhD at HBNI Mumbai, and he has done postdoctoral studies in University of Notre Dame. Now he's in Nuclear Physics Division, BRC. Now Dr. Gupta is presenting his talk. Dr. Gupta.
Hello, very good evening. Hello.
Yes.
Am I audible?
Yes, very much.
Okay. So first of all, let me thank organizers for giving me this wonderful opportunity. The title of my talk is Determination of Hexadecapole Deformation of the Light Mass Nucleus 24 Magnesium using Quasi-Elastic Measurements. This topic is one of the favorite topics of Dr. Nayak, and I have also learned somewhat about this field from him only. Thank you, sir. So maybe I will take a minute or so to share a story how we entered into this problem. So in case of magnesium 24, we observed a significant deformation effect on strength distribution of isoscalar giant monopole resonance, which is also known as the bending mode, which Professor Gar was presenting in the first talk. So are you able to see the second slide?
Yes.
Hello, are you able to see the second slide?
Yes.
Yeah, so here you can see in this figure, the data can be explained only if we assume that magnesium 24 in the ground state is prolately deformed. And this blue line, it is a calculation assuming magnesium 24 is spherical. So we can see that there is indeed a deformation effect, and it was quite surprising because magnesium 24 is a light nucleus and having a fragmented strength distribution, and it is showing a very prominent deformation effect. So from here we got the motivation to study the deformation effects of magnesium 24 using fusion barrier distribution. So in any case, we know that the nuclear chart exploration, including the regions of trip lines and island of stability, that is the primary aim of the current nuclear physics research. Around 7,000 nuclei are predicted to be bound by strong and electromagnetic interactions. And out of these 7,000, 50% are still unknown to us. What I mean unknown, their masses, their half-lives, spins, ground state deformation, etc. are still not known to us. And among these, knowing precise information about the ground state deformation of the atomic nuclei is of fundamental importance. This importance is not only because of their roles in heavy ion reaction dynamics, but also to benchmark the microscopic interactions responsible for a particular shape of the atomic nucleus. So this is a two-dimensional plot of theoretically predicted quadrupole deformation of a variety of nuclei. We know that ground state shape is governed by the interplay of macroscopic properties such as liquid drop like thing and microscopic shell effects. And in a nucleus with the partially filled shells, balanced nucleon try to polarize the core and a deformed mass distribution is achieved. So in the mid shells, mostly you will see the deformation is found, but if you see regions close to the doubly shell closed, you will find that either the nucleus is a spherical, or if at all there is some quadrupole deformation, it is a very small. At the experimental ground, various probes have been employed so far to gain the ground state deformation, such as electron scattering, lifetime measurements, Coulomb excitation, proton scattering, neutron scattering, helium-3 scattering, alpha scattering, even muonic X-rays. IVGDR is known to be very sensitive to the deformation. So, using these probes, quadrupole deformation has been determined quite precisely for a majority of the nuclei. And now, this quadrupole deformation even have been measured for some of the exotic nuclei. So, this increasing knowledge of the quadrupole deformation definitely enhance the urge to measure the higher order deformation such as the hexapole deformation, because so far hexapole deformation situation is not that cozy, primarily because of its very small value. And particularly if you go in the light mass region of 2s and 1d shell, there you will find that either this hexadecapole deformation is not measured, and if at all it is measured, it varies quite dramatically. So the question is, can we use heavy ion fusion distribution for this purpose? So before I go what is the fusion barrier distribution is, what fusion is, let us first see the sensitivity of the fusion barrier distribution to the hexadecapole deformation. So in this figure, please stop me if you are not seeing my slides. So in this left side figure, what I have shown is fusion barrier distribution for oxygen 16 plus samarium 154 for 3 values of hexadecapole deformation. Beta 4.05, this is a solid line, this is going like this, and beta 4 equal to 0, this is a dashed line, and beta 4 minus 0.05, this is a dotted line. So this calculation shows that indeed fusion barrier distribution is very sensitive to the hexadecapole deformation. On the right hand side, I have compared experimental fusion barrier distribution for the two reactions, oxygen 16 plus 186 tungsten, oxygen 16 plus 154 samarium. Just to share this two nuclei, 186 tungsten and 154 samarium are the two nuclei which are having exactly same quadrupole deformation, but we see their fusion deformation is drastically different, and that is attributed to the different sign of the hexadecapole deformation. In case of samarium 154, this is a positive hexadecapole deformation, but in case of tungsten, it is a negative. So we can employ this fusion barrier distribution to gain information about the hexadecapole deformation. Now let's move on. What is the fusion barrier distribution is, how we get it. So heavy ion fusion reactions around the Coulomb barrier, they present a classic example of the quantum tunneling phenomena. Coulomb barrier, this results from a strong cancellation of a long-range Coulomb force and a short-range nuclear force. So this is a Coulomb barrier, and this fusion reaction takes place once this relative motion between projectile and target passes through this fusion barrier. Now, in this one-dimensional barrier penetration model and applying regular boundary condition, the fusion cross-section is obtained by this simple formula, where this SL is S matrix element. Hello, it is going good? Hello?
Yes, yes. Yes, it is going fine. Go ahead.
Go ahead. Okay, thank you.
Otherwise, we will stop you.
Okay, thank you. But in Hebbian reactions, using incoming wave boundary conditions is beneficial and feasible also. So if we use incoming wave boundary condition, which essentially means that there is a strong absorption in the inner region of the Coulomb barrier and no flux returns back. So by applying this incoming wave boundary condition, we are not required to use any imaginary potential, and calculating this transmission coefficients are easier than calculating the S matrix elements. So we have a very neat and cute expression for the fusion cross section using this one-dimensional penetration model. So far so good. Now let us see its success and failure. So here I have taken from this reference this using this one-dimensional barrier penetration model. Fusion cross section has been compared for various systems. So we can see that.
Just a minute.
Tilok, you should stop presentation.
Pardon?
Tilok has been trying for presenting.
Tilak Ghosh has started presenting something.
Yes. Tilok, can you listen?
No. So please let me know when it is ready.
Okay. Hey, but pinning Yogesh is it is coming back again.
Yeah, I also pinned on Yogesh and I could get it back again.
Okay. Then now everyone has to do the same thing. Unless it is.
Yogesh, maybe you continue now then.
Yeah, that's why I'm waiting for your.
Okay, go ahead.
Okay. So in this top figure, this fusion cross section data have been compared with one-dimensional barrier penetration model calculations. So here we see that this one-dimensional barrier penetration model works well for the relatively lighter systems, but for heavier system, it under-predicts the cross-section below the Coulomb barriers. For example, this here I have shown it a more zoomed fashion in this bottom panel. For nitrogen 14 plus carbon 12, it is nicely reproducing the major data, but for heavier system, oxygen 16 plus samarium 154 below the Coulomb barrier, it start under-predicting the data. So what is the origin of this failure? So in order to understand this origin, I have plotted the fusion cross-section data along with the calculation for three samarium isotopes, samarium 144, samarium 148 and samarium 154. So, and in order to remove this trivial target dependence, data has been plotted as a function of center of mass energy with respect to individual barrier. And on the y-axis, the fusion cross-section has been normalized with pi rb square. So by doing this, this one-dimensional barrier penetration model calculation remains common for all three nuclei. So we can see that below the Coulomb barrier, they significantly vary. So this target dependence indicates that something we are missing, and this has been pointed out. Maybe the low-lying excitation during the fusion process has to be taken into account. So in order to have a direct correlation, let's see this fusion cross-section data along with this low-lying excitations. So in the right-hand most side, this is samarium 154 low-lying excited states, and this is samarium 144. So you see that samarium, among all these three, samarium 154 is showing a very good rotational band where low-lying excited states are very close to the ground state, and it's a fusion cross-section enhancement with respect to one-dimensional barrier penetration model is highest among all three. On the other hand, samarium 154, it is a vibrational nucleus, and its low-lying excited states are quite farther apart from the ground state. So it clearly shows that if we are having very, very low-lying excited states, there is a more chance of that coupling of these rotational state with the relative motion, and the fusion enhancement will be more. So it's a very good correlation with respect to that. The another way of looking to this coupling of rotational degrees of freedom with the relative motion is a classical way. So suppose both the nuclei are a spherical one, so we will be having a single
Okay,
Coulomb barrier.
Yogesh, I think just stop it for it. Actually, there are many complaints. So I request everyone to pin on Yogesh Gupta presentation, not on Yogesh Gupta. There are two in the name of Yogesh Gupta. So you have to pin on Yogesh Gupta presentation. Okay.
And please switch off your camera also. There are 3-4 cameras are still on.
Samit.
Shall I go ahead?
Just let's see whether. Yes, Ananya has written. Please pin Yogesh Gupta presentation. How to unpin the first? Again, click there. You can unpin it.
Am I too fast?
1 minute. You are saying to unpin.
Yeah, on this.
To click the pin again. I got it. Yeah.
Yes.
And now I am pinning the presentation.
Presentation. Yes.
Yeah, I got it. It's for me. It's working now. Okay. Thank you.
Okay.
I'm
So
turning off the mic.
okay. So everyone should do that.
Okay, go ahead, Yogesh.
Yeah. So I was telling.
Yes. One more.
Classical way.
Somebody was asking.
Hello.
Yes.
Hello. Suryanarayan Shastriji and Gulam Sadhu Khan, these two.
Camera should be off.
Yes, it's on. Camera is already
Yeah.
on.
Please put off your camera.
You can switch off.
I can remove him, but switch off option is not coming.
Okay.
Yes, it's
Switch
on
off
now.
the camera.
Okay. Let's start again. I think. Please start. Yogesh.
Okay, thank you.
Yeah.
Okay. So shall I go?
Yes. Yes.
Oh, okay. So I was telling that the classical way of representing the rotational degrees of freedom is in looking the potential barrier height based on the orientation. So suppose both the partners are spherical, we will be having a 1 Coulomb barrier. But suppose my target is deformed and it is axially symmetric, then depending on the orientation with respect to the beam axis, there will be a different barrier. So suppose if it is approaching from the tip side, you will be observing a lower barrier. And if it is approaching from the sideways, you will be having a different barrier. So based on this picture, you can see that during a fusion process, rather than seeing a single barrier, there is a distribution of barriers. And we know that all orientations are equally probable, but fusion cross section, it goes exponentially or with respect to the barrier height. So these lower barriers, they are responsible for the net enhancement of the fusion cross section. And based on this picture, some average orientation formula has been developed, which I am not going into that. So basically, to explain the fusion cross section data, one has to do a proper calculation by coupled channel method. So by including the vibrational couplings of samarium 144 and rotational coupling of the samarium 154, we can see that the fusion cross section data can be nicely explained. So this coupling of different intrinsic degrees of freedom can be interpreted as if original fusion barrier has been split into distribution of barriers. In this representation, the fusion cross section is given by a weighted sum of a fusion cross section for each eigenbarrier. So total fusion cross section, we can write summation over weight of W alpha and a fusion cross section for that particular barrier. So from here, Rowley proposed a concept of fusion barrier distribution. So he showed that the fusion barrier distribution is nothing but the first derivative of the transmission coefficient for L equal to 0. And that's fine, but experimentally how to get that fusion barrier distribution? Then he showed that if you do the double differentiation of this quantity E sigma, where E is the center of mass energy and sigma is the fusion cross section, then this quantity is representing the fusion cross section. And fusion barrier distribution reflect nuclear shell effects much more pronounced than the excitation function itself. So here you see that this is in the left hand side, these are the fusion excitation function, and in the right hand side, they are corresponding fusion barrier distribution. So unless in the left hand side figure, unless otherwise we do a couple channel calculation, these data are not telling us much. But on the right hand side, you see that in case of samarium, there are marked structure you obtain. So using precisely measured fusion data, barrier distribution has been determined for a variety of nuclei. So for example, for calcium plus calcium, you get almost a kind of uncoupled barrier distribution. Oxygen 92, zirconium, samarium, tungsten, samarium 144, nickel plus nickel. So these examples clearly show that fusion barrier distribution provides a fingerprint of the nuclear structure effect of the colliding nuclei. And we can invoke fusion barrier distribution to get the information about the nuclear structure. But the problem is, just a second. In general, though we have measured for a various system, but in general it is difficult to measure the fusion cross-section at the forward angles in presence of the huge elastics and Rutherford events. And in many of the cases where heavy systems where quasi-fission etc. are happening, it is not really easy to measure the fusion cross-section. So in order to overcome this problem, another method has been suggested, and a representation of fusion barrier distribution can be extracted from quasi-elastic scattering. So this is the same expression which I was showing in the last slide. You just keep in mind that the fusion barrier distribution is nothing but the first derivative of the transmission coefficient. Now, in heavier reactions, we can think of there are the total incoming flux. It goes into two paths. Either it is crossing the barrier and the fusion is taking place, or elastic scattering, or some peripheral reactions are happening, such as excitations of a projectile or target, or there is some transfer is happening. So there are two clear groups. One is the fusion and another is the back scattering. So if it is a fusion, we call that flux, that fraction of that flux is a transmission coefficient, and the reflected flux, it is a fraction of those peripheral collisions. So total flux has to be conserved. So from here we can see that R0 will be nothing but 1 minus T. So this first derivative of transmission coefficient will be nothing but negative of first derivative of reflection coefficient. So whatever we were getting using the fusion excitation function, same we can get through the quasi-elastic measurements. And what will be this R0? R0 is a reflection coefficient for L equal to 0. So that means a ratio of differential cross-section for quasi-elastic to Rutherford at theta equal to 180 degree. But experimentally, it is not possible to measure the quasi-elastic experiments at 180 degree or for L equal to 0. So we have a solution for that also. Let's go to another angle, let's say 170 or 160 degree. So there, not L equal to 0 will be involved, but there will be some non-zero L. So for that non-zero L, there will be a centrifugal correction. So if we correct for that, then we are good. So how to do that? At any moment, we can write the center of mass energy equal to this potential energy, this electricity potential energy plus potential energy corresponding to the centrifugal. So this centrifugal part is that correction energy. So this is easily can be derived using the Rutherford orbits. So this effective energy will be available energy minus this corrected energy. So now the net effective energy will be something like that. So now let's compare the fusion barrier distribution with distribution obtained from the quasi-elastic. So in this figure, in the left hand side figure, you see this solid points, they are quasi-elastic data, and open triangles, they are the fusion data. So one thing you notice that they are very much overlapping, but also there is one interesting thing they are telling that in case of fusion, you are getting uncertainties larger at the higher energies, but in case of quasi-elastic, you are getting uncertainties larger at the lower energies. Why this is so? Because in case of fusion excitation function, you know that larger yield is that at higher energies. In case of quasi-elastic excitation function, larger yield is there at the lower energy. And also, this errors is more at the higher energy. In fusion data, error is more than the lower energy quasi-elastic data. And the reason for that is because in fusion, we are involving with the double differentiation. But in the quasi-elastic, we are involved with only the first derivative. So that point I will come again when I go to the benefits. And on the right hand side, this is oxygen on samarium. This is from the fusion measurement, and this is from the quasi-elastic measurements. So apart from this a small peak in both here oxygen 16 plus nickel as well as oxygen 16 plus samarium 144. There is a small peak. This is somehow in quasi-elastic data it is smeared out, and this is basically smeared out. It is attributed that it is happening because of the neutron or some nucleon transfers. Exact picture is not clear, but that is the only difference. So this quasi-elastic measurements have been done at Trombay for various systems by the group led by Dr. Nayak. So here he has shown the Coulomb orientation effect in the oblate 28 silicon and prolate silicon 30 on indium target. Similarly, in the right hand side, a systematic study has been carried out for various projectile on thorium target. He has done for various systems. Some of them I have listed over here. So quasi-elastic barrier distribution offers several advantages over fusion excitation function. First is smaller statistical error on barrier distribution for a given statistics in the corresponding excitation function. And that correction which we were doing for the centrifugal, it is a rather benefit to us, because by measuring as a same beam energy, and if you put the detectors at several angles, you will having a data at many angles corresponding to a same beam energy. And measuring of the quasi-elastic yield at backward angles is much easier than the fusion yield at the forward angles. And experimentally, it becomes very difficult to measure the fusion cross-section in cases involving very heavy projectile and target, where quasi-fission admixtures with evaporation residue and compound nuclear fission cross-sections. Taking all these factors into consideration, we have measured quasi-elastic cross-section to gain information about the ground state deformation of magnesium-24. This experiment was carried out when I was a postdoc at University of Notre Dame. So this experiment was done at this 9 MB tandem machine. Just to share with you, this is a 9 MB machine, but this practically operates at 10 MB. So this a small area houses 3 accelerators right now. This is a 5.5 MB machine. There is one more Van de Graaff 3 MB machine. And here we measured quasi-elastic scattering data for 2 systems, magnesium 24 plus 90 zirconium and oxygen 16 plus 90 zirconium. Just to share with you, this before this experiment, magnesium 24 beam was never cooked at the Notre Dame, and they were not having any experience how to develop this magnesium 24 beam. So I wrote to our Anit Gupta ji, and he sent us full recipe, and we developed this beam at University of Notre Dame. So this is a schematic diagram of the experimental setup. We used three. Is everything okay?
Yes, okay, go ahead.
Okay, so we used 3 silicon delta EE telescope at the back angles, 138 degree, 148 degree, 158 degree. And in case of oxygen 16, we varied the beam energy from 36 to 62 MeV. And in case of magnesium 24, this was 61 to 93 MeV in a step of 2 MeV. And the target was enriched 90 zirconium oxide. It was on a backing of carbon 12. And we employed 2 monitor detectors at the 20 degree. So these are typical monitor data. As you can see, our target was having impurity of the carbon because of the backing, and oxygen 16 because of oxide. So in the monitor, this Rutherford scattering events from the carbon-12 as well as from oxygen-16 are clearly visible and they are well separated. Similarly, the case of magnesium-24, these scatterings from the carbon-12 and oxygen-16 are clearly visible. But kinematics helps us, and there is no scattering events at the back angles from these oxygen-16 and carbon-12. So these are the quasi-elastic events. Just now I am showing for the oxygen-16 plus 90 zirconium. So this left-hand side panel at 138 degree, and this medium panel 148 degree, and the last panel this is 158 degree. So at the lower energies it is okay. We are at higher energies it is punching through the detector, and we are able to reasonably separate out. But either at the lower energy or at the back angle, some of the events they stop in the delta E detector itself. So we have to judiciously put a banana gate including this zero channel and project it out on the y-axis. So you get these events. So these are clearly only the quasi-elastic events. Similar was the case for the magnesium-24. In case of magnesium-24, I was not having any plot where I was having this delta E versus E, because in every energy as well as in every angle, they were stopped within the delta E itself. So these arrows over here shows the region of interest for the quasi-elastic events. So using these quasi-elastic events and monitor data, we get the quasi-elastic excitation function. So this left-hand side, quasi-elastic excitation function for oxygen-16 plus 90 zirconium, and right-hand side, this is for magnesium-24 plus 90 zirconium. And you can see that quasi-elastic excitation function for three angles overlap quite nicely. And the shape of this quasi-elastic excitation function for magnesium plus 90 zirconium does not show any discernible difference when compared with that of oxygen-16 plus 90 zirconium. Raw data doesn't tell anything. We have to differentiate these curves and get the barrier distribution. So this is the barrier distribution for oxygen-16 plus 90 zirconium left-hand side, and in case of 24 magnesium plus 90 zirconium, it is right-hand side. Frankly speaking, before the experiment, I was hoping this magnesium 24 plus 90 zirconium, it will be showing some sharp structures, but it is not showing any sharp structure, but it is significantly broader than the oxygen-16 plus 90 zirconium. So in order to get information about the intrinsic degrees of freedom involved in both the reactions, coupled channel calculation have to be performed. So for this purpose, we have used a modified version of the code CC-Cool, and this modified code is referred as a CC-Cool. In CC-Cool, regular boundary condition along with the imaginary potential are used in place of incoming wave boundary condition. In this code, imaginary potential takes care of the compound nuclear formation and reflected waves are treated explicitly. So what are the real potentials? Real potentials are estimated using the Broglie and Winther systematics, and they are further tuned so that uncoupled calculations are reproduced, the experimental data as best as possible. So this table shows the real potential data. And for imaginary potential, as I mentioned, imaginary potential was said to be well confined inside the Coulomb barrier in order to just simulate the compound nuclear formation. Haguenau is part of this work. He has already benchmarked this set of imaginary potential parameters for a variety of systems. They work well, and it has been established that results are not sensitive to imaginary potential parameters as long as it is strong enough and well localized inside the Coulomb barrier. And this short-range imaginary potential has no influence on the quasi-elastic scattering cross-section predictions because its strength at the surface region is negligible. It is very confined. You see that its diffuseness is 0.1. Now let us see the transfer channel Q values. Fortunately, for both the reactions, oxygen-16 as well as magnesium-24, you can see the Q values are highly negative. So these unfavorable Q values show that transfer channel coupling must be relatively weak in the present reactions. It doesn't mean that transfer events are not there. We have seen in the 2D plots, transfer events are there, but their strength is not that significant. So now let's come to the result. Just a minute. So in the left hand side top panel, I have shown the quasi-elastic excitation function. For oxygen 16 plus 90 zirconium I am talking, and this is in the bottom panel, this is the barrier distribution. So first, as usual, we tried for uncoupled without using any coupling. So this dotted line is uncoupled fusion distribution, fusion barrier distribution. So this cannot explain the barrier distribution as well as the quasi-elastic excitation function. Oxygen 16, however, it is having that 3- state, but its effect is negligible. It just shifts the entire barrier distribution. It has been established. But 90 zirconium, it is having its two low-lying quadrupole excitation and octopole excitation. So if we include this 2+ and 3- state of 90 zirconium, they explain data very well, and the strengths used in this code, they are very much consistent with the data shown in the literature. Now let's go to the magnesium 24 plus 90 zirconium. So in case of magnesium 24 plus 90 zirconium, first we tried uncoupled. There is no way that uncoupled is going to explain, and then we tried with the using only the 90 zirconium coupling and considering 24 magnesium as inert. So there is no way this dotted line is this solid line where we have included 90 zirconium vibrational couplings. So there is no way both excitation function as well as the barrier distribution cannot be reproduced. So this indicating the need of including rotational coupling of the projectile. So first we tried only the quadrupole deformation. So we have frozen the target coupling from the oxygen 16 plus 90 zirconium, and now we are working on the couplings for the projectile 24 magnesium. So we first included only the quadrupole deformation. Various values have been tried out, and you can see that none of them can explain the barrier distribution. This indicates the presence of hexadecapole deformation. So first let us see whether the hexadecapole is sensitive in this case of magnesium 24 plus 90 zirconium. So first I carried out calculations for different values of beta 4. So this red line is for beta 4 is equal to 0, and this green dash dot line is for beta 4 plus 0.5, and beta 4 negative value this left hand side, and here beta 2 was taken as a reasonable value from literature 0.3 right now. So because now there is a we don't know what combination of beta 2 and beta 4 has to be taken. So to find out a combination of a beta 2 and beta 4, I varied simultaneously both beta 2 and beta 4, and for various combinations of beta 2 and beta 4, chi-square was determined in this two-dimensional parameter space, where the chi-square was defined like this. Yi is the experimental data minus this is the calculation for a combination of beta 2 and beta 4, and sigma I is the error. So here beta 2 were varied in the range of 0.2 to 0.6 in a step of 0.01, and for each value of beta 2, beta 4 was varied in the range of -0.2 to 0.2 with a step size of 0.01. So we can see this chi-square, it is showing a minima corresponding to a very small region of beta 2 and beta 4. So now our job remains to do some good analysis and to get quantitative value of beta 2 and beta 4 and also their associated uncertainties. And for that, we have used a Bayesian analysis. It is not possible to cover that Bayesian analysis within this talk.
Yeah, actually, you can go a little faster and conclude. There are questions.
Few more slides. So basically, from that chi-square distribution, we have generated a probability density distribution. So by projecting this probability density distribution on the beta 2 axis, you get a probability distribution for beta 2. Similarly, by projecting on the y-axis, you get a probability distribution from beta 4. Now from here, you can get all the statistical parameters, their mean values, their errors, and their anti-correlation or correlation. So here we find that beta 2 and beta 4 are anti-correlated with a correlation factor of -0.298, and we have determined that beta 2 is 0.43 plus minus 0.02, and beta 4, sorry, this is minus 0.11 plus minus 0.02. This is minus. And these uncertainties correspond to the 95% confidence limit. So with these values, beta 2 0.43 and beta 4 minus 0.11, final calculations were carried out, and it is seen that both quasi-elastic excitation function and barrier distributions are nicely reproduced within the experimental uncertainties. Now let us see how these beta 2 and beta 4 compares with the literature data. In literature, beta 2 has been determined using several probes, which I mentioned earlier, but beta 4 was not measured in all the cases, and in many cases the errors were quite large. So we can see that beta 2 is very much consistent, not only with the experimental data, but also with the theory of Muller and Hicks and Yoshida-san. And this was the story of the light nucleus, and earlier in the rare earth region also it has been shown that quasi-elastic scattering can be employed to get hexadecapole deformation for rare earth nuclei. So these results establish that quasi-elastic scattering could provide a useful probe to determine the ground state deformation of atomic nuclei. So summary, quasi-elastic measurement were performed for oxygen 16 plus 90 zirconium and magnesium 24 plus 90 zirconium reactions at different laboratory angles. Quasi-elastic excitation function and derived barrier distribution therefrom were compared with coupled channel calculation using the code CC pool. Vibrational channel couplings were obtained from oxygen 16 plus 90 zirconium reactions. Rotational channel couplings for 24 magnesium were required to reproduce the data, and best choice of the beta 2 and beta 4 deformation was searched for using a Bayesian analysis. Obtained beta 2 value is consistent with literature data, and we have determined hexadecapole deformation of magnesium 24 very precisely for the first time. And we would like to point out that quasi-elastic barrier distribution is especially useful for radioactive beams, with which high precision measurement of fusion cross-section would be difficult in order to extract the fusion barrier distribution. And this is also the case for fusion reaction relevant to super heavy elements. This is a very recent publication of 2020 Physics Review Letter, where this quasi-elastic scattering experiment was performed for the reactions relevant to hot fusion. In 2007, similar experiment was performed for the reaction relevant to cold fusion. So now I thank you all, and I thank all the collaborators from Trombe, from Notre Dame, and Professor Hagino from Kyoto. And this work has been recently published during the lockdown in Physics Letters B. Thank you.
Thank you, Dr. Yogesh Gupta, for your excellent presentation. And the talk is open for discussion. Any question, please ask.
Yogesh,
there are questions in the chat.
Can I ask one question?
Yes, sir. Sure, sir.
Yeah. So this was done some few years back at Notre Dame.
Yes, sir. 2015.
2015, yeah. And now have you tried to do some measurement with a different isotope of magnesium, let's say magnesium 26 or something? Although it will in intensity can be still okay.
Yeah, sir. That would be interesting to do here at our DFR Peloton facility. I'm having some more ideas to implement here, and we will be doing.
And what does one expect for hexadecapole, or as you go to more neutron-rich nuclei? So, for example, you said that for RIBs and all that it's important, but magnesium 24 is N equals Z. But when you go to a magnesium 26, you will have a different ISO spin. So it will be interesting to see if some of these ground state properties change.
Yes, sir.
And in what way they change.
So, sir, it is seen in the rare earths that here the beta 4 is plotted as a function of neutron number. But it is seen that for a lower number of neutrons, beta 4 is a positive, and somewhere in the middle it is a 0. And for a neutron rich, it is a negative beta 4. So, not many data are there, but maybe this kind of trend might be there if we go in a isotopic chain of the one element.
Yes, same thing can be done. Same thing also can be done with the oxygen 16, 18. Some of these, because quasi-elastic measurements are very simple, and one can just churn a lot of data.
Oxygen 16, 18, maybe they too light, but maybe employing a very high jet, maybe that 208, that kind of target.
Yeah.
Maybe one can
You
try
can choose
out.
the target. Yeah, you can choose the target.
Yeah,
But
yeah.
study of kind of ground state properties, especially with higher deformations, large range atomic number, will be interesting. This can be
Yeah, actually, in other than oxygen 16, even in this 2s 1D shell, there are several nuclei for them. Hexadecapole is still not frozen. There are uncertainties quite lot.
Any other questions and response?
Can I ask make a couple of points?
One at a time, please.
Yeah, IUAC Madhavan. Yeah.
Yes, sir. Yes, sir.
Yeah. Actually, you mentioned at 180 degree you cannot do the quasi-elastic backscattering by any method experimentally, but by detecting the target recoiling at 0 degree using a spectrometer, you can do which we do in our transfer measurements at 10 below barrier. That is one point. The second point you mentioned is the large source of error at higher energies in fusion method and quasi-elastic backscattering method of distribution of barrier at low energies. It's not just because the cross sections are more there. The cross sections don't change with energy much. Because of the uncertainties in the measurements, this leads to large errors. And one point I wanted to ask you, when you are normalizing that fusion cross section by pi r ED square for the oxygen on samarium, 3 different things that Australian group think.
Yeah.
If the RB is correct, then it should not exceed 1. But in those plots, I saw they are going above 1 when you're normalizing by pi r square. This is the one. So if RB is correct, that is the pi RB squared should be the maximum value to which it should saturate. But here it seems to be going above 1. Could be.
These are experimental data which I have taken from this Hagino's review article. This is a progress in theoretical physics, and there he has plotted this figure, and from there I have taken it. Actually, regarding the errors, what I was trying to emphasize is in case of fusion excitation, fusion barrier distribution, which you extract from the fusion data, the errors are large at the higher energies. And at the quasi-elastic case, this is large at lower energy, and once you go, they are keep on increasing. Keep on decreasing.
I agree with that. But it's not because of the large cross sections at those areas. It's because the cross section doesn't change.
There are 2 points over here. One is that in the fusion case, this is a double differentiation of the cross section. But in case of quasi-elastic, this is a single differentiation.
Yeah,
okay.
that is well known. The cross section doesn't change much with energy. Because of that, the uncertainties in the measurement lead to huge fluctuation. It's not the quantum of cross section. It's
differentiation means we are comparing 2 similar quantities.
Can I ask question?
Yes. Yes.
Yeah. Okay. Maybe I missed it regarding CC pool. How it calculates the elastic cross section?
Actually, there is no well-written document for that. But I discussed with Hagiro. He says that like in CC pool, in original CC pool, there is no imaginary potential. Okay, and wait a minute.
See, this is like a scattering code, na? They calculate the scattering matrix or phase shape, no? And so they calculate the scattering cross section basically. But this CC pool and although they calculate the transmission coefficient. So
this is not exactly CC pool. This is a modified code of the CC pool. This is a modified.
See, whether it calculates the PL only or it is calculating the scattering matrix or like.
No. This also gives the elastic scattering separately also. Elastic scattering separately and quasi-elastic together.
So it is a scattering code or something like.
Yes.
Like a Fresco or.
Actually, I'm not having any document for that. I asked him a couple of times, but he's also not having any code, and somehow he tells that these peripheral reactions are treated explicitly in the CCQ. But how exactly it is doing, I don't know.
Okay. Yogesh, I have a question.
Yeah.
This quasi-elastic barrier distribution is supposed to smear out the peaks or any structural effects compared to the barrier distribution obtained from fusion cross sections. But still in this paper, in your work, you are claiming that this gives much better, and the deformation parameter that you have obtained also you are claiming to have better means good data, the correctness, the uncertainty is less. So what is your comment on that? Means what I mean to say that fusion cross section is supposed to give better.
Smearing effect is more visible when there is some sharp peak. Like I was showing that oxygen 16 plus samarium 144, there is a sharp peak, and which they are assigning that this is from this plot. This is attributed to the neutron transfer. So this kind of sharp peak is there in the fusion data. Then you will see that in the quasi-elastic data, that kind of thing is smeared out.
Yes.
Yeah, that kind of things are smeared out.
Yes.
But if this kind of collective excitations are there, the collective excitations are not going to give you a sharp peak. So even if you measure the fusion data, I'm sure that we are going to get the similar kind of fusion distribution what we are getting from the quasi-elastic. There may be a very, very minor difference at the higher energy, and because as I showed here, Q values are very negative, so transfers are very, very less. And what we are seeing are on the collective excitations of both target and projectile, and they are not sharply peaked kind of nature.
That's a question from Professor Kodre.
Yeah, Yogesh, I want to ask, has anybody tried this 24 magnesium with a heavy spherical target like 208 lead?
This is my dream problem. The day energies are available, I will be the first to do this experiment.
Yeah, because that beta 2 is supposed to have orientation effects.
Actually, in India we are not having energies available corresponding to this magnesium 08. We need higher energies.
Please ask others to switch off their microphone.
Okay.
Professor Godre, this magnesium 24 plus lead-208 is the best candidate to demonstrate the Coulomb reorientation effect. And I thought initially that in case of magnesium 24 plus 90 zirconium, also I will see some Coulomb reorientation, because there was one PRL in 2003 or 4 sometime. He was telling that magnesium 24 plus lead-208 Coulomb reorientation should be seen.
Yeah, that was the TDHF calculation, and then in 2011 I showed using classical calculation that is possible.
Yeah, actually in India also we can do, but the problem is we can do using LINAC, and there is some stripper foil to reduce the energy, but the energy resolution will die out.
Yeah, my question was, is it possible anywhere else? in case you know that.
If you have bigger machines, like even suppose our this K500 cyclotron comes up, and if we have a variable energies, and as I pointed out, placing the detectors at various angles.
So I can call.
Headphone लगा
Go to Texas A&M.
Yeah, the Professor Garg can arrange an experiment at Texas A&M.
Oh, we can do that.
Okay, sir, I will come.
Okay, thank you.
Bensi, can I make a comment if everybody has done with the questions?
I have a question myself. I will just ask.
Yes, sir, please.
I will be interested to know, you showed one PRL paper, because what I understand for light nuclei, this method may be good to determine, deformation parameters.
Huh?
But deformation parameters, the way you have done.
Yes.
But when you go to very heavy system, the one you showed, that is a PRL, recent PRL. Where they are studying the fusion barrier distribution for synthesis of super heavy elements.
Yeah.
So I want to know the type of barrier distribution they get experimentally, how they are different from the one we are getting for lighter system, because they are other than just whether it is just a tunneling of barrier, or there are some extra things are coming into picture.
What they have concluded is that external barrier, the notion of external barrier distribution is still valid even for this high ZP-ZT systems. And they get some. I have not gone through detail of that PRL paper. I just saw that abstract, and they are not measuring deformation, etc. They are just trying to see the reaction dynamics through this.
I know that for such a heavy system, what you will learn is the exact barrier distribution.
Yeah, what kind of barrier, when they are colliding, when this fusion is taking place, what kind of barriers they are seeing.
Whether
That
there
kind
is
of
a single barrier or there is very broad one and things like that, because it is it's for such heavy system. Whether we can just simplify the thing the way we are doing for lighter systems, like a tunneling of barrier or coupling. They are
in general, because of large ZP-ZT, that barrier distribution must be very broader, but I have not gone
and
into
also
detail of
coupling
that.
will be very difficult to include there.
Yeah.
I just don't know exactly what they have done.
Okay, I will send you a copy of this paper to you.
Okay.
Yogesh.
Yes.
I have one point regarding magnesium 26.
Yes, sir.
Chaudhary has asked. See, this is around
Yes, sir.
abundance is around 11%. NGO if we inject, and if your energetics is really, you have to match your energetics. The NGO, in first stage you use some energy. Normally we inject MGH. So if it is MGO, if your energetics is satisfied, then the 11% abundance, as Dr. Chaudhary was suggesting, we can try out at that one.
Okay. Energetics will be fine because our terminal voltage at least 11 MB is at least there.
Then we can try.
Yeah, thank you.
That's what
Any other questions?
Yogesh, I have another question. You have measured at different angles, and we know it is the best result will get that transmission and that 1 minus R, that is supposed to be at 180 degree. So backwardmost angle, angle is supposed to be the best, but you have used 118 degree. How good is that estimation?
I understood your question. Let me tell you.
Okay.
Experimentally, we have used data only last 3 angles: 138 degree, 148 degree, 158 degree. What was the purpose of this 128 and 118 is just to benchmark. In case everything stops in the delta E detector, then really we are getting a quasi-elastic or something else is coming. So in this collaboration, there was one Chinese guy. He was very much behind me that he used 2 more thick E detector just to see that the change in energy, because in the quasi-elastic the dominant is the elastic part. So whether the elastic energy is going according to the two-body kinematics or not. just to verify for that purpose, we put two more detectors, 118 and 128. So indeed that variation in the energy was consistent with the two-body kinematics. Now, after 138 degree, I tried to include data from 128. They were not fitting into that scheme of other angles.
But even 138 and 158 suppose, or means how good the approximation is to changing to center of mass energy, that whatever formula you are using, how good that estimation is in order to calculate or use that formula of quasi-elastic distribution to Friesen distribution.
From this work's experience, I am telling that if you see data up to 138 degree, they are very much overlapping. But if you ask me quantitative line, where up to what angle it will be okay, that I am not having.
No, up to 58 also I feel that all are not good, suppose. It should be 170, 175.
Ramesh Garg is having a comment.
Oh, if everybody is done with the questions, I just wanted to make a comment with your permission.
Okay, go ahead.
Yeah, it was, I'm very proud of this particular measurement. This was done and it's an way our lab works. I was in London when this experiment was done. Yogesh was the only person. I had two other people in my group who were brand new graduate students, but the entire lab came together to do the experiment in developing the beam, in doing the experiment. If you look at the paper, you can literally see every graduate student in our lab working. So this was the kind of way Notre Dame lab works. I just wanted to give a shout out to our lab and how things work, and it turned out to be an excellent measurement overall. Of course, Yogesh didn't sleep for many days. Other people helped out.
Thank you so much, sir, for your remote support.
I heard it was done during Christmas vacation or something.
Yes, during Christmas break. We were not there. Everybody just piled up, and it was Yogesh's dedication to this particular measurement that he pulled. But there were people who really helped him, like Wang Peng, Stek, made the beam, got the thing. I think he mentioned Wang Peng who put the extra two detectors. They all came together. We weren't even sure initially we had the right detectors or whatever. It all happened during the break. And as I said, our own group was nothing. It was just Yogesh, two graduate students who had joined 4 months before. But everybody came together and we managed to do this experiment. So it's a tribute to Yogesh, but also how our lab works. I just wanted to make that point. Thank you,
Thank you so much, Ejibaz, your blessings.
Thank you.
Congratulations, Professor Garg.
Yes, it is very nice to hear that.
I'll take any compliments, but I don't deserve them.
This is for your students and lab.
My students do all the work. I just get the credit.
Trying to close for today's session. I guess we had a very good interactive session, and we continue this with the more vigor tomorrow. And the list of talks are all given, and let's assemble at 5 o'clock sharp tomorrow. And I request Sanat or Satyaranjan, Prakash, any announcement regarding conduct of tomorrow?
You can just announce the speaker for tomorrow. That would be nice.
Yeah, I have to see that actually.
Yeah, please announce.
Anyway, announcement
tomorrow
is there. Right now, I don't have it.
Tomorrow I have the names.
Okay.
I can tell that.
Yeah.
Tomorrow, first seminar is by Professor Walter Guimaras, University of Sao Paulo, and second, Dr. Akhil USC New Delhi, and third by Indranil Majumdar, EFR. We'll assemble here at sharp 5 o'clock.
Okay. Thank you all. So I'll stop here.
Sure.
And
thank you so much. we can still have some feedback how the session can improve for tomorrow.
Yeah. I think we can just talk about that. Because maybe it was good to let a speaker, they handle the